Hello, class. Let's begin our discussion today looking at a group that looks like this. And this is a methoxy group. And then that benzene derivative's name is anisole. And the cool thing about the methoxy group is that it's going to activate this ring 400 times more than if it was just a benzene ring. So if you take this and react it with any electrophilic aromatic substitution reaction, this is going to go 400 times faster than if it was just benzene. And this is the reason why is because we see lone pairs on this oxygen, and it can donate electron density into the benzene ring. So it is activating the benzene ring. There's more electron density in that ring, so it can react faster. So we call that group right there an activator. It's making it more active than benzene. A principle that we need to understand is that activators, we'll write it up over here. Activators or activating groups are going to be ortho. I didn't spell that right, did I? Ortho-para-directors. So when we do a reaction with the methoxy group on it, where is it going to put the substituents? Ortho positions or para? Now if we take, well, let's just use this. If we take anisole and treat it with bromine, look at the reaction conditions. We're going to do a bromination. I'm not using any catalyst. I don't need to use any catalyst because the methoxy group has activated this ring so much, you don't need a catalyst. You just add bromine. And so the product that you're going to get is it's quite interesting. We said it's an ortho-para director, but because this ring is so reactive, guess what? You add a bromine on the two ortho positions and the para position. It is that reactive. And it is nearly impossible to stop. You take anisole, bromine, boom, it's just going to go to this species right here. No stopping it. And it's a near 100% yield. I mean, this is an efficient reaction. Now let's take a look at a different reaction. Let's say we do a nitration. What's going to happen next with that? If we do a nitration reaction, so what are the conditions for nitration? If we take anisole, we'll treat it with nitric acid, and then you need the catalyst. A little bit of sulfuric acid, right? And so that's going to give us some products here. It's going to give us potentially 3. So that nitro group is going to go on the ortho position. You can also have very, very trace amounts, like 2% on the meta position. And let's try to squeeze this one in here. We can have some in the para position. So the ortho is 31%, and the para is, what was it, 67%. Can't see that, so let's put it right here, 67%. So you can see that the methoxy group is ortho and para directing. Only 2% of the meta. We kind of ignore that. So that's what activators do, ortho para directing. Now we can see here, in this case, that the para has a higher yield than the ortho. Recall from the other video when we just had a methyl group, these were swapped. The methyl group, we had 60+% in the ortho and then 30-something% in the para when we had a methyl group, but now it's switched. So why did it switch? Well, the quick and easy answer to that is when you compare a methyl group, okay, to a methoxy group, with the methoxy group, you now have more steric bulk. So it's a simple steric argument that the nitronium ion has a harder time coming in at the ortho position due to sterics. You can see that if the nitro group goes to the para position, stays away from the sterics, and you get more, it's just better that way and you get a higher yield. Okay. So what we want to take a look at is understanding this reaction a little bit more by looking at the sigma complexes. When we take a look at the sigma complex, it's very similar to when we had a methyl group here instead of the methoxy. But when we take a look at this, in respect to the methoxy, what we have going on here is an additional resonance structure that we didn't have before with the methyl. So those pi electrons can come in, okay, and then those would go there, and those would go there. In that manner, and what is that going to give us? That's a resonance structure. So we would have a double bond there, there, our nitro group. We have one additional resonance structure, and this additional resonance structure is very stabilizing to the sigma complex. You can see here in this structure right here how you have a positive charge on that carbon right next to an oxygen. Do you see how these lone pairs can come in and help stabilize that? So this one is very, very stabilizing. In contrast, when the nitro group goes to the meta position, there's no additional stabilizing resonance structure. With the para, we do have an additional one, and that's the electrons are going to, so the lone pair there is going to come down, and then that's going to come there like that. And then we get a stabilize, another very stabilizing resonance structure. Double bond, double bond. And the nitro group has been, let's raise this up a bit here. That's one squeaky pen. There's our nitro group, and then double bonded O. Positively charged. So here is the fourth resonance structure for the para position, and it also is very, very stable and stabilizes the sigma complex. And so this analysis helps us to understand why the methoxy group is a ortho-para director. So make sure you understand how to push these arrows and how it helps us understand the stability. When we take a look at a nitro group on a benzene ring, we can notice a couple things. The first thing that I notice is that we have a positive charge on this nitrogen. And so what that's going to do is, because it's positively charged, it's going to withdraw electron density from the benzene ring via the inductive effect. There's this positively charged, so these all these electrons in the pi ring are going to want to gravitate towards that positive charge and withdraw the electrons away. We can also see that the nitro group can withdraw electrons from the benzene ring by resonance. So we could see that these pi electrons here can come here, and then that goes like that. And so now we're going to have a double bonded nitrogen like this. You see how just by looking at the resonance structure, let's see here, that nitrogen also still has 4 bonds, so that's positive charge. Okay, not the most stable resonance structure, right? But you can definitely see that it is pulling electron density from the ring via resonance. And when this happens, you can see that the ring's losing electron density, so it's what we call is it's being deactivated. The benzene ring is being deactivated because of the nitro group's inductive effect of making the electrons go towards the nitrogen and via resonance. Now, the effect of the nitro group is quite interesting when you look at the reaction rate. If you have a nitro group, and let's say we want to do a second nitration. This is an electron withdrawing group, so it's a deactivating group, and it makes this next reaction right here go 100,000 times slower compared to benzene. Isn't that crazy? But because it goes 100,000 times slower, we need to soup it up a little bit by adding some heat. Got to give it a little extra oomph to get over the activation energy here. And when we add the heat, we are going to get a second nitration event. That's NO2. We can have ortho. We can then have our meta. And then we can have our para. Now, these 3 different products, they're not all in the same yield. And what we see is the ortho is going to be 6%. The meta is going to be 93%. And the para is 1%. So based off of that data, what can we say about deactivating groups? Deactivating groups are meta-directors. That's the major product. Now, how do we rationalize the distribution here of products? Well, we have to go back to the sigma complexes and analyze it that way, and that will explain why we get such a high yield with the meta relationship. Now when we look at the sigma complexes, when we have the ortho, meta, and para positions, we can take a look at our resonance structures, and now instead of trying to find the most stable resonance structure, like the super stable resonance structure, what we actually find is a very, very unstable. You see how we have a positive charge on this carbon and an electron withdrawing group. So that's not a good combo. Not a lot of electron density, and then something trying to suck electrons away from an atom that doesn't have very many electrons. So that's very, very unstable. But when you look at the meta position, it does not have one of these ultra unstable resonance structures. But when we look at the para, can you find the one that's ultra unstable? You see that it's going to be this one. So the ones that are ultra unstable are the ones that have a positive charge on the carbon that's attached to the electron withdrawing group. Whereas when you look at the meta position, you will not find a single one where that positive charge is directly attached to the carbon that is attached to the electron withdrawing group. So this is why we have electron withdrawing groups or deactivating groups direct the substituent to the meta position. So let's do a recap up to this point. We have electron donating groups that are activating groups, and these activating groups are ortho and para directors. We have also seen species that are electron withdrawing, which are deactivating or deactivating groups, which means that they are meta directors. Right, that's what we've seen up to this point. So I can say this with surety. If it's an electron donating group or an activator, it is always going to be para and ortho directing. Now, if you have an electron withdrawing group, more often than not, deactivating groups are going to be meta directors. There's one exception that you need to be aware of, and that is when you have a halogen. Okay, so for example, chlorine. If we have chlorine, if we try to do an additional electrophilic aromatic substitution reaction, what happens is, this is crazy, okay? Well, let's back up a little bit. The chlorine atom right here is an electron withdrawing group. And it withdraws the electrons from the benzene ring via induction. Whoa, Texas, carbon. So we know that chlorine is a very electronegative atom. And because it's very electronegative, it's going to want to pull electron density towards itself. And so as that does that, it's going to pull some electron density from the ring. So it's going to deactivate the ring by inductive effects. But then you can also see something very interesting. It has lone pairs. And so we could see a potential resonance structure where those lone pairs come in and give us something that looks like that. So we'll draw the resonance structure down here. There's a chlorine, and then the two lone pairs. Then that chlorine is what? Going to be positively charged. Now it's looking like the chlorine is an activator because it's putting electron density into the ring. So we would assume now that chlorine is an activator, so we think it's going to be a para-ortho director. But then Previously I said it actually is a deactivator. And so it's withdrawing electrons by the inductive effect from the ring. So if it's a deactivator, then it should be a metadirector. See, there's two ways to look at this, and one says this, one says that. So what do we do? So what we say, halogen, so we can replace that with an X, and that X represents all halogens. Okay? Halogens are deactivating groups, but they are ortho-para-directors. Okay? That is the exception to the rule. So let me recap one more time. So if you have activating groups, they are always going to be ortho-para-directors. If you have an electron withdrawing group or a deactivating group, then it's metadirecting, except for halogens. Halogens are deactivators, but ortho-para-directors. Now, how do you rationalize this? Well, you have to go to the sigma complexes once again and look at it that way, and that can help us understand why there's this exception. Now, what this is showing us is when we took a chlorobenzene and we did a nitration. We did this reaction right here, and then that would have given us a nitration reaction. And where would that nitro group go? Would it go ortho, meta, or para? And so that's what we're showing in the sigma complexes right here, is we went ortho, meta, and para with the nitro group. Now we're looking at why halogens are deactivators, but ortho-para-directors. So if we take a look at the ortho product, what do we see here? We see 3 resonance structures, but we are going to have a 4th resonance structure that is just really, really stable. So what we're going to have is a positively charged chlorine right there and the nitro group there, like this. So why is that guy so stable? Well, what are we doing? We are stabilizing. That would go there like that. And then those would come like that. And we would have a double bond there. There, that looks good. So we have a additional resonance structure that stabilizes that complex. So I cut off the top part right here. So what I've drawn there is a positive charge on the chlorine atom. And it would have another lone pair right there, okay? So the same arguments when we were looking at when we had a methyl group or a methoxy. We introduce a 4th resonance structure that's very stable. When the nitro group goes to the meta position, we don't get a 4th resonance structure that's very stabilizing. But we do see that with the para position, we are going to get a 4th resonance structure that is stabilizing. And so we have our nitro group here, chlorine. So what's going to happen here? We're going to have the lone pairs come down, form that double bond, and that's going to come down like that. So we will have this and that, double bond, positively charged. And so now we have another stabilizing resonance structure that contributes to the stability of the para, or the substituent adding to the para position. So when we take a look at it again in this light, you see how we have a positive charge on the chlorine or on the carbon attached to the chlorine, and same for right here. And so the lone pairs on the nitrogen, or lone pairs on the halogen, can donate in to help stabilize that positive charge there. Whereas in the meta positions, you see that the chlorine can't do that. Okay, so that helps us understand what's going on here with that exception. Please remember that is the big exception that you have to remember. Halogens are deactivators, but they are orthopair directors. We have discussed activators and deactivators at length now. Now we need to add another layer to that discussion. So all the molecules shown in green, we have the benzene ring, and instead of drawing the benzene ring over and over again, I'm just doing the pH, which represents phenyl. That pH represents the benzene ring. So all the molecules in green, they are called strong activators. Very, very strong activators. And why are these strong activators? Well, what can you notice about those green molecules that I have not drawn in? Do you see how they all have lone pairs? And so those lone pairs can donate into the into the benzene ring, and it does it very, very well. It's a strong activator. But then when you take a look at the pink molecules, these are moderate activators. Now they also have lone pairs that can be donated into the ring. But why? So if they have lone pairs just like the strong, why would we call these guys moderate? Well, let's think about this. So if we draw out the phenyl ring, okay, we have lone pairs there. So one could envision that the lone pair right here can come in and donate in like so, right? That is true. That would activate the ring. But do you also see another resonance structure that could happen? Where else could those lone pairs go? That lone pair could go and resonate that way. So yes, these are activators, but they're not strong activators because it has resonance. And so the electrons are shared between the benzene ring and the carbonyl. So they're only moderate activators. Okay? And you will see tables in your textbook that lists all the strong activators, all the moderate activators. And then you can envision what's coming next. If we have strong, if we have weak, if we have strong, if we have moderate, then we would expect that we have some weak ones, and we do. So we have some weak activators, okay? And some of those weak activators would be, that's a P there, would just be a methyl group or an ethyl group, okay? And so forth. Anything, excuse me. I don't know why I drew out that benzene, but anything alkyl, you could put another one right there. These are all weak activators. We know alkyl groups are electron donating, but there's just no comparing a CH3 with no lone pairs to a O- with a lot of lone pairs. The oxygen is going to donate way more electron density than a methyl group. So we have those three classes for activators. We have strong, moderate, and weak activators. Now, do you have to memorize all these structures? Not necessarily. If you understand the principles that I've just taught, then you don't need to memorize as much. You can see the principles where I talked about resonance. There's no resonance here. It's just the electrons can donate in. So you see some guiding principles here. Now, what we want to talk about next is looking at the classes of deactivators. Some examples now of deactivators. The ones in green are going to be strong deactivators. Nitro groups, quaternary amines, and species. The X right here represents any halogen. Very, very strong deactivators. Now, we've already discussed using the sigma complex to understand why nitro groups are electron withdrawing. You can see with the quaternary amines why that is, because that positive charge is inductively pulling the electron density. And same with the halogens. Now, the molecules in pink, what do we see here? We see a carbonyl attached directly to the phenyl ring or the benzene ring. And these are moderate. How do you spell moderate? There. Moderately deactivating. Strongly deactivating, moderately deactivating. And why would we say that they're moderately deactivating? Well, you see how we can have a resonance structure here. Let's see if I can draw it right here. If we draw a ring right there, do you see that we have a resonance structure that now puts a positive charge on the carbonyl carbon? And then so you could envision a second resonance structure where the pi electrons can donate in to help stabilize that cation. That's an R, that's an R. You can envision something like that. So that's a weakly everything in pink here is moderately deactivating. Okay. Look at this one. When you look at this guy right here, what's this group? That's the sulfol group. Amides, aldehydes, ketones, esters, carboxylic acids, nitriles, they're all moderately deactivating. So what are some examples of some weak deactivators? And those would be the halogens that are directly attached to the benzene ring. Okay. So if you have chlorine or fluorine, chlorine, bromine, or iodine, those are examples of weak deactivators. Okay? So X is going to equal chlorine, bromine, and iodine. Those are weak activators. Weak deactivators. Okay? But how do these groups direct? They're orthopara directors, even though they're weak deactivators. Okay. Now what we're going to talk about is now using all these principles that we have discussed and using them in synthesis. And so there's some really cool reactions that we're going to discuss. And what's neat about them is order matters. It's very important that you do the reactions in the proper order in order to get the target compound that we're interested in. So we'll do a few examples to illustrate that point. Let's take a look at this reaction here. We want to take this disubstituted benzene and do a halogenation. But when we do that reaction, where is that bromine going to attach? We have 4 options. Where is it going to attach? Well, the way that we figure that out is that we have to look at what's already on the ring and ask, where does this group direct the reaction to occur? So we see an alkyl group. So that's going to direct as a ortho-para. But when you look at the para position right here, it's already taken up. So the only options that we have are ortho. So the methyl group is going to want to go here or there. Then we take a look at the other substituent. That's a nitro group. That is electron withdrawing. That is deactivating. That is what? Meta directing. So meta with respect to the nitro group would be right there as well. So this one's an easy one because both substituents direct it to that carbon. So we would predict correctly that our product is going to put the bromine right there. So you could say it is ortho to the methyl group or meta to the nitro group. It gives us the same product. Or the better way of saying it is the directors direct the bromine to the exact same carbon. Okay? So that's a pretty cool one. But we will see situations in which there's a conflict. Okay? So for example, let's do that in a different color. What if we have a species like this? We have an OH, and then we have a CH3. And let's say we want to do a nitration. So where is that going to go? So the OH is ortho-para director. The methyl group is an ortho-para director. And so with respect to the, let's circle it in blue, with respect to the OH group, it's going to direct it to the ortho positions. But the methyl group is also ortho-para director. It can't direct it to the para because the OH is already there. So the methyl group is going to direct to those ortho positions. So now we have conflict here. What is going to, where's the nitro group going to attach? To the carbons pointed by the green arrows or the blue arrows? Well, we have to break the tie with all this. So we look at both of these. We identify them as activating groups, but now we have the subclasses: strong, moderate, and weak. And we can see that this guy from our discussion is going to be strong, and this one's going to be a weak activator. And so strong wins. So our product is going to be, put the nitro group there because the OH is the stronger activator, so it's going to predominate. And that right there would be our product. We could say that would be our major product. Isn't that cool stuff? So let's clean this board and we'll look at some other examples. Now, when you have a mono-substituted benzene and you want to do an electrophilic aromatic substitution reaction, typically when you have a substituent, the reaction is going to go to the para position, typically. Well, we know what para is. I'm going to say that's the major product, and this one's the minor, typically that's the case. And why is that the case? It's a steric argument. The para position is going to have less sterics. So that one's typically going to be favored when you have a monosubstituted benzene. So that's the first So we're going to go through a list of considerations when we're looking at reactions. And that's the first consideration. When it's monosubstituted, the para product is typically the favorite one, or the major product. And it's all due to sterics. Now, what if we tacked on let's see, a 1,4 disubstituted molecule, and we try to do this reaction? What is the major product going to be? So we have to modify this a little bit. Okay. So we have to have our methyl group there. We'll just go CH3 like that. Okay, so where's that nitro group going to go? We can see both of these are weak activators, so they're the same thing. So when we have this, we could put the nitro group here. Or we could put the nitro group here. So based off of a steric argument, which one would you predict to be the major product? You would predict this one to be the major product because the nitro group is getting attached to the carbon that's closest to the one that's least sterically hindered. You can see that this nitro group is next to this very sterically hindered alkyl group. So that would make this one the major product. Okay, so that's the second consideration that you need to look at. You see how we're just looking at sterics here to help us figure out where they're going to go? Okay, now what if we have something, let's just start brand new here. What if we have a 1,3 disubstituted ring? Something like that. And then we want to do a nitration. So what could our products potentially be? Well, we have those groups still there. And I'm going to just draw this bond a little bit shorter. We have that one, and then still there. Okay, so where does that nitro group going to go? Well, this is, so when you look at it this way, let's see here. Where are we going to go? We can go to the ortho position. So the methyl group has this ortho position and that ortho position. So if we highlight it, we have that position and that position right there. And then this guy has that one and that one. All right. Now the methyl group also has the option of going para, so it could go there as well. And then that one could also go, the propyl group could also direct it para. So we have all these possibilities of where the nitro group's going to go. So we could have a third option over here. So let's draw our third option here. Okay, so let's draw this one like this. So we could have that as an option. Well, let's see, we could have this one as an option. NO2. I don't like how that looks. That looks a little weird. We'll just go NO2. Okay, NO2. And then where could we have the other one? We could have this option right here. So which one is going to be the major product? Let's think about this. If we put the nitro group right here in the middle right there, it's sandwiched in between two sterically hindered groups. So that's very unlikely. So this one's not even observed. They're not observed at all. It's just too sterically hindered to get the nitro group in there. So now we just have between these two. Based off of a steric argument, you could see that this one is less sterically hindered. So this one right here would be the major, and this one right here would be the minor. Because you see this nitro group is next to the propyl group, and then this nitro group's really close to the methyl group. So it's the better option between the two. Okay, isn't that cool that we can predict these things? So here's a synthesis problem that we have to really think hard about. Let's say this is my starting material and I want to put a bromine at the ortho position. Okay, right here. How can I get it to go there? Okay. Because if we did just Br2 and our iron tribromide, what would, if that's the reaction conditions that I did, would I get this product? And the answer would be not really, because this is so sterically hindered. If we did that reaction, we would predominantly get this product, the para. That would be our major. But what if the situation calls for, I don't want the para, I want this one. And this is the cool thing, what you can do is you can block. You can put a blocking group here. Let's represent it by BG for blocking group. If you can put a group on the para position, then when you do this reaction, there's no other choice because this alkyl group is ortho-para directing, and the para position here is just taken up. So when you do this reaction, it is forced to go to the ortho position. And then what you do is after you form that product right here, you just remove the blocking group. And now you have your product, your desired product. So we just have to go back into our synthesis toolbox and say, okay, what groups have we discussed that you can put on like this, and then all of a sudden just take it off? Does anything ring a bell? Do you remember what we've talked about in this chapter? We call the sulfyl group. So what if we took our molecule of interest here and we did a sulfonation reaction? So what's the sulfonation? That would be fuming sulfuric acid with our sulfur trioxide. And because this is such sterically, it's so bulky, it's going to predominantly give us the sulfyl group in the para position, right? And then we can do the bromination, which will favor the ortho position. And then how do we take off the sulfur group? Remember, we just treat it with dilute sulfuric acid in water. And then that's going to pop it right off, giving us our product that we desire. Isn't that so cool? And that is the cool thing, and that's also the challenge, that we can't be thinking one-dimensionally, just, one reaction to get to our product. There's a roundabout way to get to our product to solve problems that we may encounter. So that is fun stuff. So that's where we will end today. And as always, if you need any help, please let me know. I'll be more than happy to.